All right, now, we use chi-square also to do something called a contingency table. In a contingency table, we're asking the question if two things are the same or different, or more things. There could be 3 or 4 or 5 or 6 things. Random in this case means the same. So we could look at a whole bunch of houses in California and Nevada and try to figure out if the two states have the same default rates. We could look at 10 states and see if the 10 states had the same default rate. I do surveys all the time on campus where we look at things like faculty who have been there more than 6 years and faculty who have been there less than 6 years, or faculty who have been there 3 years or less versus faculty who have been there 3 to 6, 6 to 20, over 20. So we have all these groups of that we can divide faculty up into: male, female, different racial groups. Whatever it is that we're trying to analyze about our faculty, we can use chi-square to tell us whether or not that different group answered the questions on the survey the same. So we can say, did men and women answer this question the same? And we can say yes or no, at least statistically yes or no. And you know how good that is. Okay? So we can draw a picture that looks like this. Okay? Now, don't just try to draw this yet. Let's go through it step by step and draw it as we do it step by step. So I have 2 states. I have Nevada and California. I have whether the homeowner defaulted on their loan or did not default. We looked at 1,000 households in Nevada and 4,000 in California. And of the 1,000 in Nevada, 600 defaulted and 400 did not. Of the 4,000 in California, 2,000 defaulted and 2,000 did not. Okay? Everybody got that. The numbers here that are underlined are the O's. Those are the observed. Okay? So I observed those numbers. I looked at 1,000 houses in Nevada and I observed 600 defaults and 400 not. I looked at 4,000 houses in California and I observed 2,000 defaults and 2,000 not. Okay? Everybody good here now. Now, I need to figure out what the expected is. To do that, I have to add the observed up across. So I add up 600 and I add up 2,000 and I get 2,600. And I take 400 plus 2,000 and I get 2,400. How do I know I did it right? Well, if I add up this way, I get 5,000, and if I add up that way, I get 5,000. So the total here is 5,000. Now, you're saying, what good does that do me? Well, it turns out, if we look at this, that's 52%, and that's 48%. You with me? 2,600 is 52% of 5,000. 2,400 is 48% of 5,000. And how do I know I did that right? It adds up to 1 or 100%. Okay? Now, you're saying, so now what I know is 52% of 1,000 goes there. 48% of 1,000 goes there. 52% of 4,000 goes there. 48% of 4,000 goes there. How's that? Okay? 52%, 52%. That's the percentage of the whole thing that defaulted. So of the 5,000 homeowners, 52% defaulted and 48% didn't. So my expected would be 52% in every box up here and 48% in every box. And they're called cells, right? So 52% of every cell up here and 48% of every cell up here. So there's 1,000. 48% of 1,000 is 480. 52% of 1,000 is 520. 4,000, 52% of 4,000 is 2080. 48% of 4,000 is 1920. Now I have it observed and I have my expected, and I can go stick those numbers in my chi-square formula. But notice now, I have 2 rows, 2 columns, 2 rows. My degrees of freedom is 2 minus 1 times 2 minus 1. And I'm not going to screw up the math this time because that equals 1 degree of freedom. Okay? So again, expected equals the percent in each row of the total divided by the total in the column. So again, 52% of 1,000, 48% of 1,000. The other way you can do it is not even bother that. If you really want to just do some math, take 1,000 times 2,600 divide by 5,000, that number goes there. Take 1,000 times 2,400 divide by 5,000, that number goes there. Take 4,000 times 2,600 divide by 5,000, that number goes there. And take 4,000 times 2,400 divide by 5,000, that number goes there, right? So this number would be that number times that number, and that whole thing divided by that number. Okay? So you either do row times column divided by total, or you do the percent in each row. Hopefully we got that by now. So we stick all those numbers in our little formula, and we get that, 32.04. Okay? What does 32.04 mean? That's right. It means nothing. We have 1 degree of freedom. The critical value is 3.84. We already looked that up. 32.04 is bigger than 3.84. We reject the hypothesis. Remember that our hypothesis, we'll draw a graph of this here in a second. Our hypothesis was that Nevada and California have the same default rate. What did we decide? We reject that hypothesis. So Nevada and California do not have the same default rate. In other words, it's not random. That means there was a higher default rate in Nevada than there was in California. So again, we have our critical value here is 3.84. We reject because we're out here. That means not random. Not random means not the same. The 2 states' default rates are not the same. They're different. Okay? So, let's try another one. Let's suppose that you're playing computer war games and there's 3 possible outcomes for people playing the game. You're playing against a friend. You can win, you can lose, or you can tie. So we separate the players into 2 groups. One group plays an aggressive strategy. The other plays a defensive strategy. And we have 500 people in each group. And the results are, in the aggressive strategy, they win 200 times, they tie 100 times, they lose 200 times. In the defensive strategy, they win 150 times, they tie 200 times, and they lose 150 times. Okay? So we're going to draw a box, right? Draw a box. Draw a box. We could do this either way. It doesn't matter. We have group 1 and we have group 2. And there's 3 possible outcomes. Win, tie, lose. Remember, group 1 is aggressive. Aggressive. That's the word aggressive. I'm sure you can read that. And group 2 is defensive. And then these numbers just go in here. 200, 100. Okay? These are the observed. All right. So is this beautiful? This is beautiful. So I did it the other way here, just to confuse you. We have group 1 and group 2. Doesn't matter which way you do it. You could do it either way. Okay? It's part of the deal here. I don't want you thinking you have to do it one way or another. Aggressive and defensive, those are your 2 groups. And the aggressive group won 200, tied 100, lost 200. The defensive group won 150, tied 200, and lost 150. And both of them, we played 500. Okay? Now we add up across. So there were 350 wins, 300 ties, 350 losses. That adds up to 1,000. How do we know we did it right? We add up 1,000 going this way, and we add up to 1,000 going that way. Now we're going to test the null hypothesis, right? That these data are random. Random would mean that we get the same results with both strategies. The two strategies end up being the same. Okay, if we reject this hypothesis, that means the strategies are different. So we need to take this, right? And we need to figure out what the expected is for each box. So this is 35%. And this is 30%. It's really easy math here I did for you. And this is 35%. Okay? So of 500, 35% of 500 goes here. Right? And that is 175. 35% of 500. Or you can take 350 times 500, divide by 1,000. You'll get 175. Okay, so here's everything filled in. 175 is 150, 175. 500 times 350, right? 35% of 500 goes both places. 30% of 500, 35% of 500. I have my observes, 6 observes, and then these guys are the expected. So I'm going to take each observed minus each expected. How many degrees of freedom do I have? Answer is 3 minus 1 times 2 minus 1. That's 2 degrees of freedom, right? I have 2 degrees of freedom. Okay? So we go look here, 2 degrees of freedom, 5.99 is the critical value, right? We could use 9.21, but let's just use 5.99, which is 95%, right? Alpha 0.05. All right. So again, null hypothesis random, alternative hypothesis not random. Degrees of freedom, 3 minus 1 times 2 minus 1 is 2, critical value 5.99. Then I take all those numbers back here, 200 minus 175 squared over 175. 150 minus 175 squared over 175. We get 47.6. What does the 47.6 mean? It means nothing. It's just our test statistic, okay? So 47.6 is bigger than 5.99. So I reject the null hypothesis that it's random, which means it's not random, and that means that the two strategies give different results. Doesn't necessarily mean one is better than the other. It just means they give different results. So one strategy is more likely to win and more likely to lose, and the other strategy is more likely to tie. So they give different results, and depending on what kind of player you are, that's how you'd play, right? So again, we have chi-square, that's 0. We have 5.99 is our critical value. We're all the way out here at 47. This is the rejection region. Okay? Easy, huh? Easy.